Hello my dear students, I warmly welcome you to CR Digital Classes. So in this lecture we are going to discussing about problem based on the orthonormal basis. So in the previous lecture we discussed about the orthonormal basis definition, orthogonal vectors definition and orthonormal set definition also. So now for the short answer purpose these types of problems are very important and this question has been repeated in the previous examination. Listen carefully. First of all, show that the set V1, V2, V3 is an orthonormal basis of the vector space R3 where the vector V1 is equal to 3 by root 11, 1 by root 11, 1 by root 11. Okay, that is the first column matrix, or we can take it as a vector V1. Second vector is equal to minus 1 by root 6, 2 by root 6, 1 by root 6. And the third vector V suffix 3 is equal to minus 1 by root 66, minus 4 by root 66, plus 7 by root 66. Here we have three vectors. Those three vectors form a orthonormal basis. So we have to show that these three vectors form a orthonormal basis. So first of all, so we need to get some little bit confusion between orthogonal basis, orthonormal basis. Orthogonal basis and orthonormal basis. The difference between these two bases is, for orthogonal basis, it is enough to show that the product of any two vectors equal to 0. Here, for this condition, if you show that V1 into V2 is equal to 0, or V2 into V3 is equal to 0, or V3 into V1 is equal to 0, then we will get that the orthogonal basis. Orthogonal basis. For the orthonormal basis, for this orthonormal basis, first of all we have to show that orthogonal basis. After finding that orthogonal basis, the resultant vector, we have to calculate the length of the vectors. Length of the vectors means norm of the vectors. If that norm of the vectors equal to unit value, then the resultant set, if you make in the flower bracket, then that set is called orthonormal basis. Okay, to form orthonormal basis, first of all we have to find the orthogonal basis and the unit vectors. Okay, so in that purpose we are discussing the definitions once again. Orthogonal set. An orthogonal set is referred to the set of vectors v1, v2 up to so on v suffix n in the vector space Rn, in which each pair of distinct vectors, okay, just observe this word distinct. Okay, whenever you take a pair of vectors, that vector should be distinct vectors. The pair must be orthogonal if and only if v suffix I into v suffix j equal to 0. That product value equal to 0 whenever I naught is equal to j. I naught is equal to j. That is the condition for the orthogonal set, and that is only orthogonal basis. Now another definition is orthonormal set. Orthonormal set is a set u1, u2 up to so on up is referred to that orthonormal set if it is an orthogonal set of unit vectors. Okay, it is an orthogonal set of unit vectors. So that is the difference between orthogonal set and orthonormal set. So now we are starting the solution of this problem. Given vectors are v1, v2, v3. Consider, first of all we are going to finding that the orthogonal basis. Okay, in that purpose we have only three vectors. Take the product of the first two distinct vectors, so v1, v2. So here v1, v2 is the inner product. So those v1, v2 are the column matrices. Then we can take that inner product to v1 transpose into v2. So therefore v1 transpose into v2 is equal to, this one is the row matrix and v2 is the column matrix. Okay, so here we have one row and three columns. In the transpose matrix of v1 we have only one row and three columns. In the v2 vector we have three rows, one column. So here number of columns equal to number of rows. So therefore we can apply the multiplication of the matrix. So therefore by multiplying this row with this column, then you will get 3 into root 11 into minus 1 by root 6, okay, plus 1 by root 11 into 2 by root 6 plus 1 by root 11 into 1 by root 6. So therefore the same values if you multiplying again, so v1 into v2 is equal to minus 3 by root 66 plus second product value 1 by root 66, the third product value plus 2 by root 66. Here 1 by root 66 plus 2 by root 66 equal to, you will get 3 by root 66. So plus 3 by root 66 minus 3 by root 66 will get cancelled. Then that RHS value equal to 0. The first product of two vectors equal to 0. Similarly, second product v2 into v3. So we can write the inner product to v2 transpose into v3. So row matrix, column matrix. Apply that the matrix multiplication, then you will get in this format minus 1 by root 6 into minus 1 by root 66 plus 2 by root 6 into minus 4 by root 66 plus 1 by root 6 into 7 by root 66. So if you multiply them, we will get in this format 1 by under root of 396 minus 8 by under root of 396 plus 7 by under root of 396. Okay, plus 1 plus 7 equal to plus 8. Plus 8 minus 8 will get cancelled. So therefore again here we are getting that product value is equal to 0. Here v2 into v3 equal to 0. Here 2 naught is equal to 3. That is a condition for I naught is equal to j, where I and j are the suffix values of the given vectors. Similarly, the last product value v1 into v3 is equal to v1 transpose into v3. So this one is the row matrix and this one is the column matrix. So apply the matrix multiplication, then we will get in this format 3 by root 11 into minus 1 by root 66 plus 1 by root 11 into minus 4 by root 66 plus 1 by root 11 into 7 by root 66. If we multiply them, we will get minus 3 by root 726 plus minus 4 by root 726 plus 7 by root 726. So therefore here minus 3 minus 4 plus minus 7. Okay, minus 7 plus 7 will get cancelled. So therefore again here also we are getting that product value of distinct vectors equal to 0. So in all three cases, so we got v1 into v2 is equal to 0, v2 into v3 is equal to 0, v1 into v3 equal to 0. So clearly it satisfies the orthogonal vectors condition. So therefore that set v1, v2, v3 is orthogonal set. This one is the half solution. So for the next half, so we are considering the first vector v suffix 1. So we are finding that the length of that vector. So mathematically that length of the vector we are writing it as in the norm format. Okay. So length of v1 is equal to norm v1. So under root of square sum of the squares of the entries in that matrix. So 3 by root 11 whole square plus 1 by root 11 whole square plus 1 by root 11 whole square. So if you simplify them, you will get 3 by 9 by 11 plus 1 by 11 plus 1 by 11. So therefore you will get 11 by 11 under root. So therefore you will get 1 only. The length of that vector is equal to 1. Similarly, the second vector length is norm v2. So sum of the squares of the entries minus 1 by root 6 plus 2 by root 6 plus 1 by root 6. Then you will get here also 6 by 6. So by simplifying them, root 6 by 6, again you will get 1 only. The third vector norm v3, same formula, minus 1 by root 66 whole square plus minus 4 by root 66 whole square plus 7 by root 66 whole square. So again simplifying them here, you will get that value is equal to 1. So for each and every vector in that given set, so we got unit vector. Length of the each and every vector equal to 1. So therefore 3 vectors, norm v1, norm v2, norm v3 equal to 1. 3 vectors are orthogonal vectors and those are equal to unit vectors. So therefore v1, v2, v3 is an orthonormal set. Since v1, v2, v3 are linear independent and these vectors forms a basis for R3. Here basis is nothing but these vectors are also linearly independent and those are the finite dimensional. Dimension of the given vector space is 3. So therefore the set capital S is equal to v1, v2, v3 is orthonormal basis for R3. So in this format we can find the orthonormal basis for any set. ఇక్కడ orthonormal basis అంటే మనం ఏమని చెప్తాం, the collection of the given vectors only. అంటే అవి ఆర్థోగోనల్ బేసిస్ అవ్వాలి, at the same time వాటి యొక్క లెంత్ అనేది మనకు ఈక్వల్ టు యూనిటీ అవ్వాలి. సో therefore then they are called as the orthonormal basis. So therefore this is the total explanation of this lecture. I hope you understood this lecture very well. So in the next lecture we are coming with next two topics. So make a perfect practice, prepare well. Until bye. Thank you.